Have you ever imagined directly telling your CAD software what to do, but it's just too silly talking to the screen? Have you ever wanted to control music hands-free, but it's not appropriate to speak out loud at a quiet place? Silent speech allows you to speak silently without disturbing the environment, which is suitable for these scenarios. In addition, silent speech can also be used in noisy situations where it might not be efficient to communicate with voice. My name is Ruidong. I'm a PhD student from Sci-Fi Lab, Cornell University. I'm excited to present our group's work, EchoSpeech, Continuous Silent Speech Recognition on Minimally-obtrusive Eyewear powered by acoustic sensing. EchoSpeech uses speakers and microphones on a commercial glass frame to recognize silent speech continuously. Silent speech recognition is drawing increasing attention lately. Before EchoSpeech, researchers proposed many solutions. Traditional approaches put cameras in front of the user to capture lip movements. Researchers from the wearable community tried putting skin contacting sensors to track major articulator movements such as the tongue. More recently, researchers put sensors at less obtrusive locations to capture more subtle articulator movements such as the chin, the jaw, or the ear canal. Many of this work achieve impressive performance. However, existing solutions are still limited in many ways. For example, video-based solutions are usually not portable. Many work uses obtrusive form factor for better performance, which might not be comfortable to wear, especially for long hours. Most work can only recognize phrases spoken separately instead of continuously. Some work uses cameras for better performance. However, they usually consume a lot of power and are not privacy aware. In addition, many work require users to, for example, sit still or speak slowly in order to ensure good performance. These issues limit wider applications of existing silent speech solutions. To address these challenges, we propose our solution, EchoSpeech. So, how does EchoSpeech work? We notice that facial movements, especially lip movements, are highly informative in inferring speech content. We put two pairs of miniature speakers and microphones on either side of a glass frame. The speakers emit inaudible signals which travel across the face in different paths through reflection and diffraction. We analyze the received signals from different paths and calculate the echo profiles as the representation of facial movements. We then stack the multi-channel echo profiles together and feed them into a customized deep learning model. The model has a ResNet 18 backbone followed by a one-dimensional average pooling. The pooling is only conducted on the spatial axis to preserve temporal information. Then a fully connected decoder with CTC loss is applied to enable continuous recognition. Predictions are first made on a 192 milliseconds level. Blank labels are used so that the model can automatically detect when the user is speaking without prior segmentation. Raw predictions are combined to generate continuous predictions. In addition, we designed a two-step training scheme where we first pre-train a model with other users' data. When the new user wishes to use the system, we only need to fine-tune the existing model with the new user's data. This not only saves training time, but also improves the performance. EchoSpeech can work when the user is sitting still or walking around. To compensate for the noises caused by environmental reflection when the user is in motion, we applied data augmentation. We take the echo profiles calculated when the user is static and the echo profiles of pure motion noises without speech. We linearly combine them to generate the synthesized echo profiles of speech while in motion. We then use the synthesized samples to train the model. We also applied a similar protocol on environmental sounds to improve robustness against acoustic noises. Specifically, the signals used by EchoSpeech are all inaudible. Low-frequency ranges containing human voices and most environmental sounds are filtered out before being used by EchoSpeech. This preserves privacy. We implemented the sensing system onto a commercial glass frame. In addition, we implemented a low-power variant with only one speaker, with the sensing and data transmission system operating at 73 milliwatts. We use BLE to transmit data from the glass frame to a smartphone in real time, where the entire data processing and deep learning pipelines are implemented. Compared with previous work, EchoSpeech has a lot of advantages. It uses a minimally obtrusive form factor while operating at low power and preserving privacy. In addition, EchoSpeech can recognize continuous speech spoken at a normal speed without pausing. We also demonstrate that EchoSpeech is robust to various noises. So, how well does EchoSpeech work? For evaluation, we mainly focus on the performance, robustness, and training effort. To evaluate EchoSpeech, we designed 2 command sets. The first one includes 31 words or phrases in 4 categories: music control, smart interaction, digits input, and voice assistant. To examine how EchoSpeech handles continuous speech, we designed a second section, connected digits, where we randomly generate 3 to 6 digit sequences for users to speak continuously at normal speed, such as 123, 67295, but silently, of course. We conducted 2 user studies with 24 participants in different scenarios. Results show that EchoSpeech achieves 4.5% word error rate in recognizing discrete speech. As background knowledge, the acceptable word error rate in face-to-face human conversations is usually considered to be around 5%, but of course with a much larger vocabulary, which is the next step for EchoSpeech. For continuous speech recognition, EchoSpeech still achieves around 5% word error rate. What's more, we demonstrate that the performance is consistent for speech at different speeds and lengths. In the user study, participants spoke at as fast as 113 words per minute, while EchoSpeech still achieves a 6.1% word error rate. We then evaluated the robustness of EchoSpeech in different scenarios. We demonstrate that, with proper data augmentation, EchoSpeech achieves consistent performance when the user is sitting, walking, or in different noisy environments. In order to achieve such performance, how much training data is needed from each new user? We examined the performance curve when different amounts of training data from the same user are provided. We demonstrate that the performance of EchoSpeech improves with more data. However, with only 6 to 8 minutes of training data, EchoSpeech can still achieve 10 to 15% word error rate. This gives users flexibility in customizing their own system. Finally, we demonstrate how EchoSpeech works with real-time demos. In this demo, less than 2 minutes of training data was collected from this user to recognize 8 commands for music player control. The model was pre-trained using other people's data and fine-tuned with this user's data. In this demo, less than 5 minutes of training data was collected from this user to recognize digits of any combination, any length, spoken continuously without pausing. With such capabilities in discrete and continuous silent speech recognition, EchoSpeech can be used in various real-life applications. For instance, EchoSpeech can be combined with stylus input to use CAD software smoothly without a keyboard. In addition, EchoSpeech can support hands-free music player control. Or silent passcode input. We believe that EchoSpeech takes a solid step towards a minimally obtrusive wearable silent speech interface for real-life deployment. This work is supported by the Information Science Department at Cornell University. We also thank all participants and reviewers for their support. Thank you for watching. For more details, please refer to our paper.